So I'd like to do another circuit example that has a number of dependent sources, and in this case, current sources that are dependent on a voltage. These come out a lot of different circuit types, so I just want to kind of walk through an interesting case, but also add a few other pieces and wrinkles in it. So this is going to be a case of I see two dependent current sources, both dependent on voltages, V1 and V2. I also have two resistors. I have 5 volts across this line. Okay. I'm going to care about the output voltage here. The input voltage is over on this node, and it's sitting on top of 2.5 volts. And you're thinking, this is a really interesting circuit. How do I begin to think about this? Well, certain things will come to you immediately. One is that V1, which is this term, is Vn plus 2.5 volts. V2, by the way, turns out to be, this is 5 volts. It's 2.5 volts, so it's going to be 2.5 minus Vn. An interesting approach to kind of look at this. And I could go through and I could actually go ahead and solve all the way through this circuit just using those elements and then coming up with expressions and then solving it. But I'd like to do something a little different here, and I'd like to again use superposition. Superposition is just like this really cool technique to kind of deal with all these circuit elements. So what I want to do is I want to say, okay, for case 1, I want to turn on the 2.5 volt and the 5 volt source. In case 2, I just want to turn on Vn. Okay, why would I do that? Well, this is a very typical approach that we find in classical electronics, where I might have certain elements like the 2.5 and the 5 volt source to kind of set up what the circuit's doing. And then I might have another element which is actually the signal, and I'm going to look at how the signal propagates to the output voltage. So part of it's going to be where does the output voltage sit with the structure around it, say 5 volts and 2.5 volts, and then the other one is what happens to any change from there. Everything is linear, so I'm allowed to do all of this. So if I'm looking at case 1, I can basically turn off this dependent source and see what I would get. Well, if I look at V out, I can basically look at effectively KCL at this node and solve. I get two currents coming in here. Both of these are 2.5 volts across them because there's no V in. So that turns out to give you these terms. And then I get element from these resistors here is going into this one, which is where the V out over R1 comes from. So it gives me the expression down here to work with. And so then I can imagine I would get some particular voltage from there. Voltage out is a result of all of these terms. Well, then case 2 is I'm going to be talking about V in and turning off the 2.5 and the 5 volt source. These are going to both just be shorted. Well, in that case, V1 is the negative of V2, which is then V in. So these two current sources look like they have a very similar structure, but just with a minus sign difference in it. And so instead of them looking like I've got this one minus this one is the current coming out here, I've got like this one plus this one is the current that comes out here. That definitely changes a lot of different possibilities. And then that goes into V out, which is actually a parallel combination of R1 and R2 across it. And it gives me a very nice structure for V out over V in is minus the two current source parameters and the parallel combinations of the resistors. Well, I can put in some values into all of this, and let's say I make the two GM values equal and the R1 and R2 100K and 200K. You know, what I look at for case 1, I would have it be 1.67 volts is where it'd be sitting. And I probably could measure that because I would probably just see that in a typical circuit. But in case 2, what I notice is that V out is like minus 133, so a big change in V in. That probably means that's going to be a small V in change. It's going to give me a big V out change over some region. And that turns out to be very, very interesting, right? So it's going to, but it's also negative. In case you're wondering where did I come up with this particular circuit, it actually turns out to be the operating behavior, the operating regime of a CMOS inverter through its transition region, when it goes, say, between a 1 and a 0. And so this input voltage would end up being, you know, a small change in this input voltage is a big change in the output voltage in that transition region. Very similarly described to what I would see by this gain structure. But again, even though you look at the circuit and first think there's all these different pieces, remember there's many ways to solve it. And even though I gave you one approach, there's so many different ways that are all consistent. So find the way that work for you, and that's what you want to be utilizing.